okay with you? Is this lecture going okay with you? Is it hurting you because Siddharth is now looking for participants? He is not getting too many. Is it incomprehensible or it is too easy? Maybe I don't know. Please share your experience. How is it going? No response.
Also, Supriya, maybe they can also tell whether they are not getting enough time because of the quark matter related things or something like that.
Yeah, I don't know, but strange that there is no response. Yes or no, positive or negative. That's something very strange.
It is okay, sir, for me.
Anyway, so we have come a long way, starting from the statistical methods, starting with single data, and then how are these probabilistic approaches going to help us in analyzing the data? Why these distributions? Only we have discussed about the most commonly used distributions. Of course, there are other probability distributions too, but these three distributions which we discussed are the most commonly used ones. And how they look like, what are their properties, how are they going to help us in our measurements. And then we in the second section of the lecture, we tried to discuss about the uncertainties, how they creep in. And this is, of course, once again, I would like to remind you that uncertainty is an integral part of the result. No result is believable without any uncertainty, no experimental result. It is not mathematics that you can calculate and say that this is my answer, 1, 2, yes, I mean, some number, that's it. This is experiment, and in experiment, the result, people will not trust the result which does not have any uncertainty. So however small it is, there has to be some uncertainty. I mean, there is some uncertainty in any kind of measurement. And so we just have to learn how to compute this uncertainty. If we know any way to minimize this uncertainty, we have to approach that way to minimize the uncertainty. And finally, along with the result, we have to quote the uncertainty. So we discussed about precision and accuracy. What is accuracy? And in context of that discussion, we kind of, I think I tried to convince you, and I hope I have succeeded to convince you that although we call it an error, it is not an actually, it is actually not an error, it is not a mistake, it is not a blunder that you are getting, but it is the more appropriate term would be the uncertainty in the result. So, and then we try to figure out how we measure this uncertainty, how we quantify the uncertainty for a single measurement, for single variable measurement. And then if we, I mean, in most of the real cases, we do not really measure one variable, we measure more than one, more than two variables, and then these variables are related to each other in some functional way, and to finally give rise to the final measurement. And if they are related to each of them, all of them in a particular functional way, how the uncertainties in these individual measurements finally comes into the final measurement. So this was about the error propagation, and today I will try to discuss about a kind of finding a relation of our measurements, and let us go there. So we always call it least square. Why is it called least square? First of all, let us see what is the relation between two measured quantities. We make a series of n measurements with pair x. So let us take one pair only. So xi and yi, where I runs from 1 to n. So just n measurements of xi, yi. So for each particular xi value, we get yi for each particular measurement which is designated by I. And we have n number of such measurements. So our object is to find a function y, that is function of x. I mean, you can call it function of x, you can call it y of x, that kind of describes the relation between these two variables. That's what our object in many experiments. Okay, so for this, first let us consider that that they are related in linear way. So let us start it from very simple. So they can have higher order relationships, higher order functional relationships, but in this case, let us start to think that they are related in a linear way. So we can think of many simple experiments where the functional relationship between the dependent and the independent variables can be approximated by the form y of x is a plus b of x. You all know this equation, right? This is the equation of a straight line. So our job then is to determine the values of the coefficients a and b. So if we know a and b, we get a definite straight line. So this equation 55 is an equation of a straight line where there are two unknowns. So a and b are the coefficients, and if we know a and b, they will define a straight line. So I am talking about a situation where you have in your x-axis the independent variable, in the y-axis there is the dependent variable, and you have a number of measurements falling on your paper, falling on your note sheet. But then you need to find out a straight line which best describes the data. Okay, the relation you can see by your own eyes that they are following some sort of straight line behavior. So, but your job is to find one straight line which describes the data the best, and that straight line will be defined by the coefficients a and b, right? Then let me take a small detour from this problem. So we had a problem that we have n number of y measurements, the dependent variable which depends on n number of x, and we want to find out a straight line. We have assumed that this is they are related in a linear way. So our job is to find a straight line with the a and b coefficient known, so that there is a definitive straight line. So let us take a detour from this thing at this moment. We will come back at the end of this discussion. We will slowly, you will realize that we are coming back to this problem, but at the moment let us take a detour and let us discuss about a kind of method which is called the maximum likelihood method. You will know why the name is such in the course of the discussion. So we have argued always from the very beginning that for a Gaussian probability distribution, the most probable value is the mean. So you all know that Gaussian distribution in a graphical way is a bell-shaped curve, and the most probable value is in the middle of this bell-shaped curve. The top of the bell corresponds to the mean value, mu, right? Okay. Can we find the mean value of any known probability distribution? So we all know that for Gaussian it is the mean, but you all know that the mean is not the most probable value for many other distributions like Poisson, like Landau. You all work with Landau distribution at least in the beginning days of your research. But in that case, it is not the same. The MPV is not the same as the mu. So can we find the MPV of any, if we know the probability distribution? Of course, if we do not know that, we cannot. But is there a way to find the MPV for any known probability distribution? Let us discuss that. Let us start with a set of assumptions. The assumptions are, the first one is we have made a set of n measurements, x1, x2, x3, up to xn. And the probability distribution function that gives that describes x is given by x. f of x and alpha. What is this alpha? This alpha is, if you now recall your definition of the probability, all the time, all of them, the binomial, be it binomial, be it Poissonian, be it Gaussian, is defined by some parameters. Okay. Now let us assume that this probability distribution, for which we have to define, we have to obtain the mean most probable value, is defined by f of x and alpha. So practically, our job is to determine the value of alpha. If we know what is alpha, then we know what is the probability, what is the most probable value, what is the probability distribution, and then we from this probability distribution we can find the most probable value. Okay, that is what is the parameter. The alpha gives the most probable value of the probability distribution. Now you can see the probability of getting the value x1 within a small interval of dx is this. This is the definition of the probability distribution. Same thing happens for x2, x3, and xn, right? So this comes from the probability distribution, because we have assumed that all these measurements, they follow a single probability distribution, which is defined by f of x and alpha. Okay, then the total probability of getting x with this x1, x2, x3 values is the product of all probability, right? So I had just taken the product of all the probabilities, f of x1 alpha dx, f of x2 alpha dx, f of x3 alpha dx, and so on up to the f of xn alpha dx. So you can take this dx, which is same for all, and it comes out to be, if you take a product, it comes out to be dx to the power n, which, so dx is same and n is another number. So this is sort of a constant number, right? The rest of the thing which comes before, which is written before the dx to the power n, is a function. So f of x1 alpha into f of x2 alpha into f of x3 alpha up to f of xn alpha. Okay, so what to do with this? And see that I have written this whole quantity with curve L. Okay, and this is the function which is called the likelihood function. This function can be written in a like you have sum. This is a product. So the product runs from equal to 1 to n alpha, and this function, this L, is called the likelihood function. Now we are slowly going into the name maximum likelihood method. So our job is to maximize this alpha, because this is the probability. This is practically this L is defining the probability, and our job our job is to actually maximize the alpha, or so maximize the L or the probability distribution. That is what is our most probable value. Our job is to find the most probable value. So where the probability distribution maximizes, that is our problem. And practically, if we can find the maximize L value for whatever alpha the L is maximum, then our job is done. See, if we take logarithm, the product changes to sum as log of L equal to so you know that a log of a into b is log a plus log b. So log of L in this case will be a summation instead of the product, okay, on f xi alpha. Fine. Now which value of alpha actually maximizes L or log L? It is the same thing. Okay, so that is why this entire method is called maximum likelihood method. So our job is to find the value of alpha that maximizes the value of L or log L. How do we do that? So we know this is again very basic mathematics, that you take a derivative. Sorry, this is del alpha. So you take a derivative of log n L with alpha, because alpha is the parameter you are trying to find out, and it to 0. That is where the L or ln is maximum, right? So that's, you put the value of ln from this. So actually you have to solve this equation to get the alpha, del alpha of log ln f, which is the function of xi and alpha, is equal to 0. You take the sum because it's a sum, and that will give you the value of, if you solve this problem, this equation, that will give you a value of alpha where ln L is maximum. This is very simple. It's finding maximum or minimum. So solution of the equation 57 gives us the value of parameter alpha, which provides the best probability or the most probable value, right? So how do we do that? How do we approach this? Let us test our solution with a Gaussian probability distribution. So we now know that if we solve this equation, if we get the value of alpha from this maximization equation, that is del alpha del ln L is equal to 0, gives us the value of alpha, which actually finds the maximum value of the probability distribution. So let us test this solution which we got with a Gaussian probability distribution, because we all know Gaussian is very simple, it is known to us. Then let us see what value of alpha we get from, if we start with a Gaussian probability distribution. So for a Gaussian probability distribution, f of xi alpha is defined as this. This we all know that Gaussian probability distribution is defined by this. Okay. So for Gaussian distribution, the maximum likelihood function takes the form. Now we have to define L for this function. What is the function L? So what you do is you take L as the product of this, right? That was the function. Then you see this is a constant term, which if you multiply, so here is a sigma I over here. Okay, if you take this product of this term, it will finally boil down to 1 by sigma of square root 2 pi to the power n, because n times you multiply. Then you have exponential x1 into exponential, because this is a product, exponential x2, exponential x3, like this up to the exponential xn. Okay. So now we go back, we are going back and forth. So this is a product. Then for exponential, a product practically boils down to a sum. Like for logarithm, it is the same thing. Okay, e to the power a into e to the power b is equal to e to the power a plus b. So that's exactly what I am writing here, that L becomes this constant term into exponential of sum over half xi minus alpha by sigma square. That is because of the Gaussian probability distribution. Okay. Now to maximize the value of L, we obtain alpha. To maximize the value of L, we obtain alpha, and to get the alpha, we want to get the alpha, we have to write in this way, that del NL del alpha is equal to 0, which is this. Okay, right? So you got it, right? So this is del alpha into this entire form which we brought this, because this it was to the power n. So n log n, you have taken log, so it becomes n log n, and then exponential becomes this power of the exponential, because you have taken log. So this term is equal to 0. Okay. So now this is a constant term. Okay. So first term, derivative of the first term is 0. So we are left with only the derivative of the second term. So half, again it is just equal to 0. So half goes away. So we are left with a sum derivative of with respect to alpha of a sum of xi minus alpha divided by sigma square. Okay. So then sigma is once again a constant, but 1 by sigma square. So half 2 sigma square goes away. So we are left with xi minus alpha square. Okay. So then I take del alpha in between inside this arm. So you have to make a derivative, take a derivative of this, which boils down to this, and then you see this is a fantastic result. You all know this, right? Now I want an answer. Alpha equal to 1 over n sum over xi, I to the power I goes from 1 to n. What is this?
Mean.
This is the mean, right? So we did not know. So we all know that the most probable value of a Gaussian probability distribution is the mean. But here we try to derive why it is so. I mean, if it is so, then can we mathematically prove it? If we do this maximum likelihood, if we follow this maximum likelihood method, we the Gaussian probability distribution, and we find alpha is actually equal to the mean, which is the most probable value. So our sort of axiom which we took, that the maximum likelihood method gives the most probable value of any distribution, is true. We have got it, right? Let us come back to our problem to determine the coefficients of equation 55, which was the straight line equation. So I took a detour. Now I am going back to this through the maximum likelihood method. Okay. Let us come back to our problem to determine the we left it unsolved.
Hello.
What is the value of A and B? Yes.
I have a question.
Yes.
In the you have defined L as a product of f of xi and alpha.
Right.
So in that case, we have a discrete distribution of xi.
Yeah.
So in place of a continuous distribution, what will be the definition of L?
It will be for a continuous distribution. This definition, your summation changes to integral.
No, but the product changed because that is product of f of xi and alpha, right?
Yeah.
In integration change to in summation change to integration, but product change to what?
Why should the product change?
No, can you go back to that slide? Yeah, here.
Where? Here.
Yeah, the function L is this on the first
Yeah.
line. So in case of a continuous distribution, if you don't take log, then continuous distribution can be integration here. But here
Yeah,
in the
I am
first,
not. So that is why, that is exactly why I am trying to maximize L and L, not L.
okay.
That is why I take log and then it becomes a summation, which you can change it to integration for a continuous distribution.
Okay. Yeah.
Is it okay?
Yes, yes.
Yeah, that's a trick I am making, that maximizing L and maximizing log of L is the same. So that's a trick I am making here. I am changing the product to summation, which you can replace with integration in case of a continuous distribution. That's a good question. Thank you. So our job was to determine the coefficients A and B, and that's what we will do in the next transparency in the slides. So we can assume that each individual measurement follows a Gaussian probability distribution with a mean and a standard deviation. What we are doing, we are not going away from our problem, because you see, when I said that you have measurements of y as a function of x, each measurement you have made for certain number of times, right? It's not just one measurement. You define an error or sorry, uncertainty of each measurement, and this is Gaussian. So each point, so when you plot your data, each point has a statistical uncertainty. And we always talk that we argued in the last classes that the statistical uncertainty you can get from Gaussian probability distribution. So each point, it follows a Gaussian probability distribution with a mean and standard deviation. This is not wrong. So if we assume that, okay, so the probability is given by this. This probability is a probability of finding A and B. We will do that because your A and B is actually here. So your yi is the individual measurement, and y0 xi, y0 as a function of xi, that's the mean. And this mean contains your, because this is, see again, try to visualize, we are trying to find a straight line which is going through the points. So there comes the mean, and this mean contains your A and B. Your y0 xi is actually A plus B xi. Okay, and sigma I is the standard deviation for each individual measurement. Is this clear? This is the starting point. If it is not clear here, we will be lost. Is it okay? So now I need a response from at least some of them that this is okay. This up to this part is okay. Should I repeat it, or it is okay?
It is okay, sir. You can continue.
Okay. So each point is a Gaussian distribution, follows a Gaussian distribution with a mean and standard deviation, and the mean is given by your y equal to y0 within parenthesis xi, that is equal to A plus B xi. Okay. So this is our probability distribution to start with. We need to find the values of A and B for which the L or the log L of this probability distribution is maximum. That's our job. And if we find that, that will give us this straight line. So how do we do it? The probability, the total probability for all n these numbers. So this I runs from 1 to n will be this, right? That is the product of all probabilities. So if you do that, it comes out to be like this. You put the probability, pi probability here, and that comes out to be like this. This is simple. So maximizing p actually means maximizing the sum inside the exponential, which we define by this thing, right? If I go back here, if I have to maximize this, it's actually minimizing this exponential has a negative power. So if I can minimize this probability will be maximized, right? That's what I am doing, and I am calling it this. And this left side symbol, this is what is called chi-square. Okay, and you see, minimizing this, and this gives rise to the name least square. We started this discussion with a promise that we are discussing least square fitting. Where was least square? So this is what is least square. Okay, so minimizing this sum is finding the least square. Why? So the question is why it was called least square. It is exactly because of this, and here I am substituting the value of y0, which is, I said, A plus B xi. Okay, then we obtain the values of A and B responsible for the minimum chi-square by solving the following equations, right? So del chi-square del A, del chi-square del B, which is given by this to 0. So if this is 0 and this is 0 simultaneously, then we find A and B. So we have two equations and two unknown. No problem, right? We needed two equations for two unknown. So now we have actually two equations and two unknowns. So for simplicity, let us assume that the error in each individual measurement is the same. So for simplicity, although it is not true, for each measurement the error may not be the same, but for this case we are learning things. So for simplicity, let us assume that the two the errors in these measurements are the same. So in that case, it boils down to these, the last two equation boils down to these two equations. Okay, I just to take the summations out and then I equate it to 0 and we get these two equations. Okay, then these are a set of two linearly independent equations with two unknowns, and if we write them in matrix notation, this is the equation we get. Okay, both equations involve A and B, and from this matrix notation we get this, and if you solve this you get the value of A and B. Okay, if you solve this you get the value of A and B, and that is your least. So once you get the A and B, you get a straight line which fits all your data with the least square, because you have done a least square. Okay, is this okay? So this is why we call it a least square, and this is exactly what your computer does when you run a fitting with a straight line. With a straight line, if you tell you give your computer the data points, you get your root or any plotting software, you give your data points and you tell it to fit with a straight line, and this is exactly your computer does. It solves these two linearly independent equations. So set of two linearly independent equations to get your value of A and B. Of course, in that case your errors are not the same, so you get a little more complicated result. So you need a computer to do that. I mean, in your school days, you usually took your eyes as the best measurement. You took a mean value from both the point, I mean, all these points, and drew a straight line. But these days, at this higher level, you don't do it. You rely on a computer, and in that case, and of course, in your high school days, you had sigma is equal to 0 because you did not put any error bar on your measurements. So here you have error bars. So if you have errors, then the sigma will be different for different points. So here I have taken out the sigma completely, that saying that the error in individual measurement is the same. And so this is, and this is least square fitting, how the A and B is determined. And this is not only true for a straight line, this can also be extended to polynomial. We derived it for the simplicity for a straight line, but this can be done for a polynomial also. So I think I will stop here. Today's discussion is a kind of a little short, because I did not want to go further unless there is specific requirement, because this kind of gives you the basic understanding of the statistical methods, the probabilities, the uncertainties, how to measure uncertainties with single variable, how to measure uncertainties from different measurements, and how from a given probability distribution we can find the most probable value, which is actually which will finally give us the least square straight line, or for example, or for that matter, polynomials. And I think rest of the things are very specific. Somebody is doing some analysis, it becomes analysis specific, unfolding and Gaussian techniques, etc., etc., etc. So the basic idea of this discussion is now kind of complete. So I will definitely, I am not saying anything new. this material of this entire lecture is based on few books. I mean, there are other books too, but most of the contents of this material has been taken from these 4 books: Statistics by Barlow, Statistical Methods in Experimental Physics by Frederick James, Introduction to Error Analysis by, once again, by Barlow, and the Data Reduction and Error Analysis, which is a very popular book among experimental physicists, is Bevington. Okay, so I will then stop sharing my contents, and maybe if there are some questions I can take. Any feedback? And of course, I have received, I think, one email which I have not opened from Rupomoy, but I did not receive the solutions of the problems I have given. So if you are doing it yourself, it's fine. Your solutions. Siddharth.
Thank you, Supriya.